Hello dear students, this is your course instructor Asif Javed. In the last lecture we did the basic of vector spaces. I told you what is the definition of vector space and various concepts that lead to the concept of vector space. In today's lecture we will be doing some properties of vector space. These are the properties that we will be frequently using while dealing with this concept of vector spaces, and moreover we will also discuss at length the various examples related to the vector space. So let me first of all tell you something about the properties of vector space. So let us consider that V is a vector space, our field F, then various properties are satisfied. What are those properties? The first property is that if you multiply any element of the vector space by 0, then you are going to get the 0. So this is the first property, and it can be easily derived because 0 into V can be written as 0 plus 0 into V, because 0, if you add 0 to 0 you are going to get back 0. Now if you use the property of vector space, then 0 dot V, this is plus 0 dot V, so that means this is again equal to 0. So this is 0 dot V is equal to 0. Now coming to the second property says that if you multiply the 0 vector by any scalar from the field, then you are going to get back 0 only, and it is again easy to prove because lambda into 0 can be written as lambda into 0 plus 0. Now that is equal to lambda into 0 plus lambda into 0. Now from cancellation laws you can easily get that lambda into 0 is equal to 0. So this is how we can prove it. Then we have another property in vector spaces, that if you multiply a scalar with a vector and if that product is equal to 0, this implies that either scalar is equal to 0 or vector is equal to 0. Again you can easily prove it. Let us suppose that lambda is equal to 0. If lambda is equal to 0, then we have nothing to prove. Now let us suppose that lambda is not equal to 0. If lambda is not equal to 0, that means it is a non-zero element. So if it is non-zero element, then we can actually take the inverse of it, because this comes from field, and in case of field every element, every non-zero element has a multiplicative inverse. So this means every non-zero element of field has a non-zero multiplicative inverse. So lambda has a multiplicative inverse as lambda inverse. So multiplying on both sides by lambda inverse, and we can actually it is very judicious to use the multiplicative inverse of lambda because it comes from the field, and moreover it is a non-zero element, so we can take multiplicative inverse of it. So on taking multiplicative inverse on left hand side we will get identity. So identity into V is equal to V, and on right side we will get 0. So V is equal to 0. So we have proved that either lambda is equal to 0 or V is equal to 0. Coming to the property number 4, it says that lambda times minus of vector is equal to minus times minus lambda times of a vector is equal to minus times product of lambda and vector. Again this is very simple to prove, as you can see the proof which is given below. Various properties from the definition of vector space have been exploited here. So lambda into 0 is equal to 0, this is from the first or second property. Now 0 can be written as V minus V. Now making use of definition of vector space from scalar multiplication, we can use that property and we can arrive at this. Similarly we can prove others. This is not too difficult to prove. Now coming to some standard examples of vector space. Let me first of all take one of the most important example of vector space, that is if we take any field and we multiply that field with itself n times, that is f raised to power n, and this basically consists of the n tuples. That is if I am taking r raised to power n, then it consists of what? It consists of a1 into a1 comma a2 comma and so on up to an, where a1 a2 an come from the real numbers. So this field can be varied actually, this can be any field. So I am taking this set of n tuples and I am taking the same field. I am actually taking a field, I am multiplying that field with itself n times, and after that I am taking the same field. So I am taking that set over the same field for which I am multiplying that field n times. So I will prove that it is a vector space. Now when I have to prove that it is a vector space, what I have to prove? Firstly, I have to prove that under addition it is an abelian group, and I have to prove that under scalar multiplication it satisfies certain properties. So let's start. Let's first of all consider the addition properties. If I take any two vectors, suppose v and w, I am taking, see carefully, if you see carefully, I am taking two vectors v and w. So if I take these two vectors v and w, and if I take their sum, then their sum will be equal to like this, because whenever we multiply two tuples, then what we are actually doing, we are adding the corresponding tuples. So we can add a1 to b1, a2 to b2, and so on, an to bn. So v plus w will look like this. Fine. Now clearly this is also an element of the vector, because if a1, b1, a2, b2, an, bn all are the elements of field, and we know that inside field the closure property under addition is satisfied. So all these elements are coming from the same field. This goes to show that this belongs to f raised to power n. So that means what? That under vector addition a closure property is satisfied. Now coming to the second property, that is scalar multiplication. This is our internal composition. Internal composition is there. Then we have to see whether external composition is also there. For external composition, what we have to do, we have to take any vector and we multiply it with any scalar, that is from any element of the field. So if we do that, what we are actually doing, we are multiplying any vector with any scalar. So this will look like this. This will look like this, and this again is an element of the same set V. So external composition is also defined. Now similarly you can easily verify that associative property will be there under for n tuples, associative property will be there, then additive identity will be there, because additive identity will look like 0 comma 0 comma 0 up to n times, and all the zeros will come from the field. Moreover, additive inverse will be there, because if you will take any a1, a2 up to an, then you can always have minus a1, minus a2 up to minus an from the same that set of vectors of those n tuple sort of vectors. So if you will add those two elements, that is going to give you back identity element. So that means additive inverse will be there, and moreover commutative property will be there, because if you will add n tuples in any order, that is not going to affect your answer. So that means what? This set under addition is an abelian group, and scalar multiplication is also there. Now we have to actually verify certain properties. The first property is this one, that lambda 1 plus lambda 2 times v. If you go on doing this, this is very easy, then you can easily find out that this is equal to lambda 1 v times lambda 2 v. Similarly, there are other properties, those are also easily satisfied for this, like you have properties lambda into v1 plus v2. You can easily verify that that is equal to lambda times v1 plus lambda times v2. Similarly, you can see that for any vector you will always have 1 dot 1 comma 1 comma 1 comma 1, this belongs to fn, and if you will multiply any element with for any vector you will always have one belonging to field. You will always have one belonging to field, such that 1 into that vector will be always equal to the same vector. So you will always have the unity. So unity will be there. So if we see carefully, actually if you take that associative sort of property, that is lambda into, suppose let me take two scalars, lambda and nu into v, and that is will be equal to lambda into nu into v. So you can actually open the bracket in any order. So that property is also getting satisfied. So all in all, we see that all the properties of vector space are getting satisfied, and this shows that this set of n tuples, this will form a vector space our field F. So from this very example we can actually construct n number of examples, like we can change a field and we will get an example. If we take field equal to R, then we will say that R raised to power n, our R, this is a vector space. If we take F as C, then we will say that C raised to power n, our R, this is a field, and we can take n as anything. We can take n as 1, 2, 3, 4, 5, any finite number, and we will always be having that as vector space over that field. Like R to R, C100 C, R over R, here we are taking n as 1, here we are taking n as 2, and here we are taking the set as set of complex numbers, and n we are taking 100. So from this very example we can conclude that all these are vector spaces. So this is the very first example. Now there are other examples also, but I will confine this lecture to this example only. In the next lecture we will explore some more examples. Thank you very much.